Hi everyone, thank you so much for coming to this session. We know that this is the last session of the day. We are the last thing standing between you and the apero. We cannot promise that this will be short, but at least we will try to make it at least as much fun and entertaining as we can for this rather complicated topic. And my name is Alina. I work as a developer advocate for GraalVM at Oracle Labs.
I'm Alfonso Peterssen. I work on the GraalVM project on Project Espresso, something I enjoy deeply. It's a meta-circular JVM written in Java. It's called Java on Java. It's a very amazing project, but this is not the topic of this talk. So,
unfortunately, we will not talk about Espresso today in this session, but please do catch Alfonso during the breaks. Espresso is a great project and very interesting to talk about. And if you have any questions, comments, feedback for us, or if you want to contribute to the project we will show you today, you can find us on GitHub or any kinds of social media and just provide that feedback or ask us questions. Okay, and this is what we will cover today in this session. Let me just remove my laptop from the way. Okay, all good. So in this session, we will talk about implementing an LLM inference engine and exactly implementing it yourself, DIY. So this will not be your yet another session about how you can use OpenAI or Gemini or any other kind of cloud-based LLM. We will talk about how you can implement such an engine yourself and only using pure Java. Moreover, you will be able to use it locally, so even in cases where you don't have internet access, maybe you are traveling or maybe you're in some restricted environment, you can still run such an inference logic yourself on your local machine, and you only need CPUs. So quite often you will be told that you need GPUs if you want to run any kind of LLM AI workload. We will talk about that, we will talk about speed, and we will talk about whether or not you truly need GPUs to run this kind of workloads. And lastly, we work on a compiler, so we care about performance a lot. So we will talk about how you can use the latest Java APIs and also use GraalVM to make such an engine fast. And with that, we want to start a little bit of history with how Alfonso started this project and what gave him the idea.
right. So once upon a tweet, Andrej Karpathy, a well-known figure in the AI world, just published this. Like he created over the weekend a version of the Llama architecture in pure C. So it's just a single C file with all the matrices, all the operation, the tensor stuff to run the Llama 2 architecture. So if he did it in C, can we do it in Java? So 2 weeks later, I ported his code to Java, and actually I managed to make it say competitive with the C version, in the sense that it was running mostly at the same speed. At the time, this was July 2023. It's already been a while. The model we could run was Llama 2, the 7 billion parameters. And is the very interesting detail here. So like it ran at 1.5 tokens per second. So you might imagine this is not very usable because it's too slow. So I kind of shelved the project and said like, yeah, maybe this is not as interesting as it may seem. But then something happened. So which brings us to today. So this is the current state of the project. After Llama 2, of course, there was Llama 3. So I went to this podcast with Adam, and he said, yeah, you should try to implement this. It's very cool. You can do it in Java. And actually, the newer version has some improvements, some new features. For example, so let me just give you a bit of an overview of what the project is. So Llama 3.java is a single file, Java file, that it contains all the features, all the components necessary to run inference from the Llama models. For example, it contains the tokenizers, it contains the parser for the GGF format, which is the one used in Llama CPP. Of course, use the inference code, the quantizations. Here in this slide, this is only Q8 and Q4, but we also support float 16 and bflow 16. And so on. So there's a bunch of extra components to load the models, run the models, and actually provide little tiny utilities to actually chat with the models. By the way, this is a thank you to the work of Karpathy, and it supports a subset of what Llama CPP supports. So it's the same file format, the same architecture, just a subset.
So again, about this setup, right, as Alfonso said, this is just one Java file and it contains the entire inference logic. And to make it work and to make it into a proper engine, you also would need a model file. So you will need a pre-trained model. And this talk, we will talk about inference. We will not talk about training. But as far as inference goes, the logic is implemented in Java. And then with the actual model file, you get a complete engine.
Right. So before starting, let's just make a clarification. there's this term called like small language model, which I don't think, or small large language model, which I don't like. So I prefer this not so large language model. For the CPU use case, something like 16 billion or more, we consider rather large. So we won't cover larger models. In this, you can run them, but they are like slower. So we consider something like this, the minis of LLM. So some models are tiny, but not that tiny. So they still have pretty smart. They have some capabilities. They can do some tasks for us. But even more, we have here the scooters of LLMs. So those are like even tinier models, and of course less capable than the bigger brothers, but still you can perform a bunch of tasks like, I don't know, sentiment analysis or spam filtering or whatever, just with the advantage that they run very, very fast.
Yeah, and this is a little joke here to make a point that LLMs are everywhere. Since we first gave the talk, I think it's even more the case. Then whenever you go, you will notice that LLMs are everywhere. You cannot even go and like online shop without LLMs trying to help you, whether you want it or not. And it got to the point where people kind of exploit them by having those LLM assistants and telling them, instead of asking questions about those products, they do things like, can you give me React code for this or that web applications? Because those LLMs are everywhere and you can do all kinds of things with them.
Right, so there are some vendors for the different models. So these are like the smaller models. You have like Facebook, Meta, Mistral, Microsoft, Llama, Alibaba, Google with the Llama, so Alibaba. So there are a bunch of different models with different licenses. They are all like cousins, let's say. So like they share like similar architecture and so on. So you can just pick the one that suits you more. But even if you don't go and download the model will come to you. Somehow. So in this case, for example, Microsoft is shipping RWKV, which is an inference engine on Windows. So with the purpose of running some inference there. If you own an iPhone, Apple is also shipping a model with your phone. So maybe now you still have to download it when an update or something, but maybe in the future, when you buy an iPhone, the model will be included already in the iPhone. And of course, if you use Chrome, of course, Chrome has also a model embedded within. So it's an experimental feature, but the whole idea is that you can perform some queries and some questions like locally. It has access to your HTML and your pages, so you can do certain queries with the model completely locally without going to the Google servers. And so if you don't use a Windows or an iPhone or Apple device or Chrome, your IDE comes with a model. So like IntelliJ comes with a very tiny model for the line completion feature, which is awesome. So it's already included in the IDE. So again, all these come bundled with the programs. You don't need to download them or anything like that. And finally, of course, if you have tried the Devox Genie plugin, you can, it's an assistant for IntelliJ. You can use it with the Anthropic models, the OpenAI models, but also with the local ones. So you can set up a local server and actually run your entire system fully locally. Right, so which brings us to the first demo of the day. So I will give you a quick tour on the repo. So the repo here, it looks something like this. As you can see, there's a single Java file, everything else just like jars and compiled versions and so on. So, but the whole point here is that there's a single Java file. So the way we run it, because I use JBang, we can do something like llama3.java. We need to specify a model. Let's just pick the llama 1 billion parameter and then just chat, so something like this. Right, boom, there we are. So this puts us in chat mode against the model, so we can say like, hello, right? Hi, who are you? And so on. Right, you can see like you get like 56 tokens per second, it's pretty fast. And this conversation is stateful. So every interaction you have with the model, everything you said before is contained in the context. Right. So let's quickly take a look at the code very quickly. I want to show you. So it's a pretty big file. So here's the header. This is for JBang. But there's no external dependencies. Everything it is used here comes from the Java standard library, which is something very nice because it's something maybe you could not do in Python, in the sense that you need like NumPy or PyTorch or whatever. But in this case, it's like just regular Java code, plain Java code using Java APIs. So The file on its own is like 2,500 lines, which you may think, oh, it's a rather large file. But it is actually smaller than, I don't know, the string class, the class, the system class. Is in similar ballpark to array list, the array list class, right? And it's heavily commented out, so I have plenty of comments. It's mostly for educational purposes, but it implements everything. So you have the parsers, all the quantizations, the vector implementation for the tensor operations. So then the whole inference package is included in these 2,500 lines. Well, I don't want to show you around because we are a bit short on time, but yeah, that's it. Let's just continue.
Cool. And this time I even remember that I need to open my slides and scroll to the point where we are transitioning. Let me just make sure we can transition because this has been tricky today for some speakers. Let's see if it works. Yay, works. Cool. So we did a quick, brief demo of Llama 3.java, and we will do more. But before we do, we want to give you a bit more information. Why would you do it this way, and what are the benefits that we see of implementing LLM inference engines exactly in this way in Java? So first of all, why local LLM inference? There have been quite a few LLM talks today here at Worksday Zurich, and some of them talked about running specifically LLMs locally and what would be the benefits. And one obvious benefit is privacy. So maybe you have all your own privacy concerns, or maybe there are some kind of privacy policies coming from your employer saying that it's forbidden to use cloud-based LLMs. You cannot load your code, you cannot load your data, you cannot use any of those LLMs in your work environment. Or maybe you just don't trust those LLMs and don't trust those vendors, and you would prefer to run something locally. So privacy is one big concern. Another big concern is cost. So if you especially have a larger project and you need a larger context window, it might get expensive at some point to interact with those cloud-based LLMs when you hit those limits and it starts to get costly. So if you can run something like that locally, and especially for like testing and development purposes, if you need a good enough, a functional enough LLM for just local development purposes, this could be greatly beneficial over cloud-based LLMs. And the last thing is control. So instead of going and talking to somebody else's API, you have your own local process that you can fully control, that you know exactly what it does. You can give it more or less resources. You can do caching. You can control the overall process. So this is why we would do local LLM inference, and now also why would we do it in Java specifically. So first of all, we are Java developers, and we are at a Java conference. We love Java, so why not do it in Java? And also we believe that Java can be as performant as native code, which we will hopefully show in our benchmarks. So that's why we did it in Java. But another benefit that I think is quite important is the project, as we showed you, is just one Java file. There are no native dependencies. As you might know, some languages and some projects would use native dependencies to speed up those performance critical parts of program. And while there is nothing like inherently wrong with that, if we can do the same thing but still within the Java world and with easier setup, we would much rather prefer that over having native extensions. And the last thing, developer productivity, we can use our favorite tools and IDEs, we can pull libraries that we need, or we can integrate our project into existing Java projects, and this way have access to the whole Java developer ecosystem. So if you were to implement something similar to what we did, or if you were to use it as, let's say, educational exercise, what are the parts that you need, and how would you implement such an engine, and what are the key components?
Right, so the inference part is just one tiny component. So the inference means the logic where you input like a vector and a vector of probabilities comes out. So that's kind of the core component, but there are a lot of components around it to run the entire inference. For example, you need to tokenize the input. So because the LLMs do not understand words, they understand tokens. So tokens just a mapping between half words or semi-words into integers. So you need a way to transform a string into a set of token IDs just to pass to the model. And of course, this is different across vendors. There's also a parser for the GGF format, there's one in, I think in Python, there's one in C, but of course there was none in Java, so now we have one.
And it's also open source.
Yeah, so it's all open source. You can just use it there. It's actually pretty easy. The format is very simple. It's very nice. And yeah, the prompt. So every single vendor has different ways to prompt the model. So prompting in this case means that you need to prepend certain tokens, control tokens, to say, okay, the model, this is the user asking a question, then you put a special token to say, now it's your turn, model, to answer that or to start inferencing. And then the model has a token also to stop. So all these special tokens and formatting and it's just a complete mess, and every vendor has different approach to do that. In the case that if you miss one space or you have one space too much, actually the model can perform poorly compared to the correct format.
That part seems hard to implement.
It's trial and error. Right, and finally, the sampler, which is an opaque component of the whole process, but there's this very fine line between hallucination and creativity, right? So it's very hard to know when you have creativity or when the model is hallucinating. But the sampler is a way to kind of tweak the outcome. For example, if some parameters you may hear, like temperature or top K, top P, are ways to control how the sampling method behaves. For example, sampling in this case means you have a probability for all the tokens. So a probability that a token is the next one in the sequence. And when you sample, you can either pick the maximum probability, or you can give the model more leeway to pick, maybe not the top most likely token, but maybe throw a dice and pick one among the 7 the topmost probable tokens or something like that. And that gives the model a little more ability to, be more creative if that's what you're expecting. But at the same time, it's more prone maybe to hallucination and something like that.
And I find sampler to be a particularly interesting part of the implementation detail, because you would think, for example, that you always would want to choose the most probable token, right? So if maybe you want to be very precise and always choose the token with the highest probability, but that might end up in a situation where you end up at one word, let's say it's cat, and then the next most probable word will also be cat because it's the closest to the previous one. Right. And this way you end up in this endless loop where it's like cat, 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 cat. And although it sounds cool, endless cats, it's probably not what you want from your LLM engine. So that's why you can balance this creativity and preciseness. And according to Alfonso, this is a very easy slide to understand. Nothing complicated is going on there.
Right. So this is the classical transformer architecture. This is a very mathy-looking, scary-looking formulas. But I can guarantee you that every single line you see there can be translated to very reasonable Java code. I'm like, this is for granted. For example, the matrix multiplication. By the way, during inference, you only need matrix vector multiplication. You can see here, it's, as you might have seen in university or in school, it's just 6 lines of Java code. There's really nothing there that is super complex. Next one is the rotational positional encoding. Something that also looks a bit scary, but actually it's just a rotation using complex numbers. So there's nothing there that cannot be implemented in reasonable Java code. So I can guarantee you that anyone maybe in this room can understand the whole logic of the inference of the compute graph, because basically you just enter a vector on the top, and then this vector you multiply by some matrices, you normalize it, and do it again and again, and at the very end, whoops,
sorry,
you get a distribution. Yeah, so at the very end, you get this large vector where basically for every token you get the probability, and that's the probability for that token to be the next one in the sequence. Unlike the general beliefs that the models only give you one token that is next, actually no, they will give you all the probability for all the tokens all the time. Right.
So we covered the part that is actual inference, right? And now going on with our implementation, we want to talk a bit more about weights and models, right?
Yeah, right. So models, you might think like, yeah, we're these 5-dimensional tensors. How do I? No, actually, the format, so the way that the models are encoded, or the tensors they use are mostly matrices, and that's it. So just a few matrices and some vectors, but that's all. So. And of course, there's this particular feature of inference. Inference means like the prediction, where every time you want to predict a new token, you have to read every weight. So for example, if you have a 4 billion parameter model, you have to read every single parameter exactly once. So there's no room for reuse or caching or anything. So imagine if you are mad that the model is like, I don't know, 8 gigabytes in size, and you have to download that from the internet. Well, imagine your computer that has to go through 8 gigabytes of data on every single token it will predict for you, right? So it is a little bit expensive. It's not, of course, not comparable to Bitcoin mining because computers are actually very good at this. So they are made for this. They're very, very fast, but still is very compute intensive.
Yes. So this was about model and weights, and we want to talk a bit more about performance now, and namely the throughput of LLMs, right? So if you were to say what is the limiting factor and what is the defining factor of inference performance, what do you think it is? And you can just shout from the room.
Come on.
We can also give you a tip. It might be in the hardware direction.
What is it? What? Well, CPU or memory bandwidth. Which one? Right. Okay. What? Could be.
Good.
And anyone else? Well, like floating point, I don't know, throughput or something like that. The flops? No?
Okay, this is our answer.
Right. Right. So memory bandwidth, you guess it. So, and there's one little detail here is that your hardware actually can be very capable of reading a lot of data very fast, but your programming language needs a way to actually take advantage of that hardware. And in the case of Java World, we use the Project Panama with the memory segment APIs and the vector APIs to actually push the program to be able to fully utilize the hardware.
Yes, so our conclusion from this slide is to address that point that you might or might not need GPUs to do LLM inference. The key thing is memory bandwidth and how well you can utilize it. So if you can do the same on CPU, if you can fully utilize that memory available to use through CPUs, you can also have a very fast LLM inference. The key thing and the key thing Alfonso wants you to remember from here is memory bandwidth is the answer to everything. And talking about memory bandwidth, we want to talk about some devices where you could be running inference on and how they compare, what kind of performance you can get out of them.
Right. So here you can see a list of devices by price also, right? So like the regular...
Well, I guess by performance, but also by price.
Yeah. And the last one is actually more than 10 times more expensive, by the way. So, but the interesting part here is that your regular computer may have like 50 gigabytes per second. So you have to do your math. If I can do 50 gigabytes per second, and my model is I don't know 5 gigabytes in size, then you can do at most 10 tokens per second. It's very easy. Usually, compute power or the CPUs are not the bottleneck. With maybe 4 cores or maybe a little bit more, you can saturate the bandwidth of a dual channel computer. But more interesting here, servers. So we're saying that you want to run these models locally, but locally means within your application that is running on a server. And servers usually have more bandwidth. They usually have like 16 channels or something. So basically, if on your machine you can have some throughput, some tokens per second. If you run the same model locally on your server, then you will get even more tokens per second because the servers have a lot of memory bandwidth available. Even the low-powered ARM cores can fully saturate the bandwidth of the server. So this is just basically for free. You don't need special GPUs or anything.
Right.
Right. So and on that topic of bandwidth, here you can see this chart is for GPUs, but for CPUs it's very similar. On gray, the gray line means the compute power, the flops on hardware over time, which you can see increase faster than the blue and green line, which means the memory bandwidth. So recently, so like GPUs, you have like, I don't know how many thousands of CUDA cores and so on, but the memory bandwidth has been stagnated for some time. The same story happens for CPUs. And another detail here is that 90% of the whole inference in Llama 3.java is spent doing one single operation, which is matrix times vector. So this is a trivial operation. We can just see here, this is what it is, right? Just like 6 lines of Java code. Of course, this is not the way we implement the multiplication, but you can have an idea that if you manage to, so everything else doesn't matter. So everything else means the attention is almost irrelevant. The softmax, the normalizations just account for 10%. 90% of the whole time you are is spent multiplying big matrices times tiny vectors, right? So if you manage to improve the runtime of this operation, basically you can speed up your inference time.
Right, and we talked about memory bandwidth and how this is one thing we need to remember if you want to have a faster LLM inference engine. And it seems like the solution, if you want to have more performance, would be to get more memory bandwidth. So by getting more resources or by getting better resources, better machines, or it seems like that could be another way to go around it. And if you could have smaller models, such as if you could have models containing smaller weights to encode each of the values, you could have better performance with the same existing implementation just because your weights are smaller, so you can go through them faster with the existing hardware. And as an example, as a metaphor, we can use this picture and different levels of compression.
Right, so like who can tell me what you see there? Is it mountain? You can just chart. Mountain, like a waterfall? Yeah, good guess. So, but, right, so as a human, you can barely like see, you can guess somehow, but you're not very sure. So, and by the way, this is 4-bit per pixel. So every pixel is encoded using only 4 bits. Now, if we give more information to the pixel, so now we have 8 bits per pixel, now we can start to see some colors. And now as a human, you can actually understand what's in the image, a rainbow. And that's it. There was no waterfall, no mountain, nothing, just a plain rainbow. And this is actually the full quality image. But the whole point with quantization is that if you quantize too much, even you as a human lose the grip of what you're observing. But if you quantize just right, you can still distinguish in the middle image that it's a rainbow. With the models, it's exactly the same thing. So if you quantize too much, if you reduce the information too much, the models also lose the capabilities, the grip to know what's going on. But if you quantize right enough, the model can still preserve their capabilities while being actually much smaller in the weights.
Yeah, and here as a human being, I think you can agree that third image barely adds anything for you in terms of value compared to the second one. It is a bit more clear, but there isn't that much added value compared to the second one, which is perfectly reasonable for understanding. And this is also similar to what we'll be talking about quantization with the models and the weights, because you can quantize them just enough so they provide value. And if we were to use those images as a metaphor, it's not like we are removing pixels away from the image and like losing the meaning and the essence of that image. We are just compressing the weights within each pixel so the meaning remains, but we are just using fewer resources to express that meaning. And we wanted to transfer what we talk about performance into kind of human perception, right? And when we talk about LLMs, the metric that we use for performance is tokens per second. But that's a bit hard to grasp as a human being because, as we said, token can be a word, a syllable, one character, any number of things. So it's kind of hard to say if you were to define what is a fast LLM, it's kind of hard to measure it in tokens per second. And for that, we will map it to our kind of idea of human understanding. But before we do, there are 3 bars on this chart. So the first one, we have model with the weights that are not quantized at all. So they're just the way they are, let's say, if you get the model from Hugging Face. And there we're using 16 bits to encode the weights. Now, in the one in the between, we're using 8.5 bits. So we are using compressed weights. And suddenly we get almost, not exactly, but almost twice the speed because our weights are smaller, so we can go through them faster. And then by using even less, so by using 4.5 bits, we arrive at 11.11 tokens per second. So the speed increases significantly just because we can go through those weights faster. But this is still in tokens per second, and how does that map to our human perception of speed? So we did a little bit of what we call napkin math, and we arrived at this conclusion that if you want to implement such an engine yourself, what you should be aiming for is starting with, let's say, 5 to 8 tokens per second, and then this will be the minimal acceptable rate for human perception, where let's say your model will be providing output and it will not look to you like it's lagging or it's too slow and it's annoying you by the delays. So anywhere between like 8 to 5 is a minimal good accepted rate, and obviously higher than that will be better. So as high as you can go, but at least 8 to 5 tokens per second. And keep that number in mind because we will do performance benchmarking down the line. Now, what? Yeah.
Go ahead.
No demos yet. No, you'll gather. Yeah. So super quickly, because we're getting closer to the implementation and to GraalVM, which we also want to talk about. So again, why in Java? Because Java can give us high performance, either in JIT, as we all know, or in native image with GraalVM that we will also show in this presentation. And as we said, with Java, and especially with the recent versions, we now have very nice, very rich, very pleasant to use APIs that especially give us ability to work with those compute-intensive and data-heavy operations such as LLM Inference. We have a nice ecosystem, so we have all the tools and libraries and frameworks at our disposal, and we can have more control over the inference process, such as we can do some caching and we can do additional optimizations coming from GraalVM to make the whole inference process even faster. And where we are with GraalVM on this, because yeah, as we said in the beginning, we both work on GraalVM, so obviously we wanted to bring GraalVM into the play, but this is not a sales pitch. It actually does bring very real value to this project. Before we go in, so where we are with the latest API support in GraalVM, we need 2 key APIs from Java. That is FFM for actually working with our model file, and then the vector API to make all those operations faster. So both of them are supported on GraalVM on both JIT and native image. So you can use in both JIT or native image modes. You need to pass additional flags and unlock experimental options because those are moving targets. We still work on our support for those APIs, but they just work. And actually, we have an update for you. So last week, we released GraalVM for JDK 24. There are updates related to FFM and vector API in that release, but also in the upcoming release 25 in September this year, we will have even more support for FFM, especially for platforms like Mac OS ARM and Linux ARM. So if you are doing development on those machines, if you're a lucky owner of, let's say, Apple Silicon Mac, you also will be able to develop such applications and natively compile them locally. And we added a lot of support for the vector API in GraalVM, specifically in 24 release. And that's thanks to our amazing compiler team, but namely Yurenko, who did a lot of that work and fixed a lot of bugs for us so we can run Llama with GraalVM and with native image. So why on GraalVM? So GraalVM is a JDK. We can run inference on JIT or we can run in native image. And we did some measurements. And what we noticed, and this is a slide that we showed when we first talked about this project at Davos Belgium in October last year. So we had a number where we said we are 15% faster on GraalVM, on Oracle GraalVM JIT than on some other JITs that you might find out there. But since then, we actually did some more work, and now we are 20% faster. So if you want to have very fast inference, Oracle GraalVM is the way to go. And if you want to try to replicate the things that we did today, you can get the latest GraalVM builds from SDK Man. You can pull 24 that we just released last week. But I would recommend that you pull even early access builds of 25 because we keep adding new support and new features. So and those are already available. So you can just go ahead and get 25 early access builds. Yes, and native image. We said GraalVM works on JIT, but also works in the native image mode, where we can ahead of time compile applications to native executables. And there was a session about this from Thomas an hour ago in the same room. Hopefully you were there, so you know all about native image now. But a key thing that you need to know, and that is relevant to this project, is the native image has this very interesting programming model where you program in Java, but then you can also benefit from native images ahead of time optimizations. And it's not only ahead of time optimization and compilation like you would do with normal Java programs, but what we can do with a project like ours, we said that those model files are very large, right? And some time that you take in the beginning when you run your program is spent parsing that model file. So because of native images ahead of time kind of nature and compilation, we can parse that file's metadata when we are building the native executable, and then we can completely eliminate startup. And by completely, I mean 0 milliseconds startup. So now with all that chatting and promises, let's see it in action. Okay, this should be good enough. So here I'm running on GraalVM and on latest and greatest, so GraalVM for JDK 24. Now that I think about it, I should also switch to 25 as I told you, but this will do for now. And I'm in my project folder already, so I can trigger my build by running make native. And this will look at my make file and will pick up this native image command. I'm running this on a remote instance because I love my Mac, but I prefer developing on a Linux instance. So if you notice any delays, this is not a delay coming from the LLM, this is a delay coming from my cloud connection to a remote instance over Wi-Fi, but it's going okay so far, so let's see. And under the hood, this triggered a native image build with a few additional commands. So the options that we are passing here is to unlock experimental option, use vector API, use the FFM API. O3 that means optimize for peak throughput. MARC native means use the specific hardware features of this machine rather than target compatibility. And we are just passing a few additional flags to make the APIs work. So this compiled in 33 seconds. I would say this is quite good. And the result of it is here in the same folder, and this is my freshly compiled right now file Llama3. It's only 23 megabytes, so it's quite small. So now we can run it by doing Llama, Llama3, and this is the file. And then I need to pass the model, and I only have this one here, so we will pick it up, Llama-3 something, and then we can do chat. And it starts, and we can do the standard thing. So we can do hello. Yeah, we can do the same. What are you? So it is quite fast. Remember how we told you that you should target somewhere between 5 to 8 tokens per second at minimum. So here we are even at 40 tokens per second, which is pretty good, right? So it starts and it works, but this is, as you can see here in the beginning, I would bet you didn't notice it. I also barely noticed it, but there is this, what we call startup overhead of 1 second. And Alfonso decided that this is unacceptable and we can do better than that, and we can eliminate that 1 second of startup overhead. So I will not recompile again, but if you wanted to eliminate that startup overhead, what you can do is build a version of your application by pre-parsing that model file. So I'm again running make native, only I'm passing one additional parameter, and I'm saying I want to pre-parse this file at the build time, and this will include the metadata for my model as I'm building my application. And this way it will once again produce a native executable that I have already compiled here. It's called Llama3 IoT, so I can distinguish between them. And this is a specialized version of a native executable specifically for that model. It's still compatible. It will run on any other model out there, but it will be super fast with that model for which we pre-baked metadata within the file. So to show that super fast, I run it. Oh, I ran the build. No, go back. I want to actually run the compiled one. I think that will be it. And I just need to pass the other file, Llama IoT. So now there is 0 millisecond startup, and it's still functional. We can still talk to it. We can say hello. We can do, I don't know, what do you, okay, it's slow because my machine is not connecting. What do you know? Okay, one last try. What do you know about Zurich? And it replies very fast. So, and now it also has 0 millisecond overhead. So even that 1 second, which I would argue was not annoying, is possible to eliminate it away completely because of what native image does, we eliminated that startup overhead. And this is something that only we, like Java and native image, can do because you cannot do it in any other ecosystem or tooling because you need specifically Java's programming model and native images ahead of time compilation. Okay, and let's go back to the slides. We don't switch now, or do you?
No, not yet.
Yeah. Okay, demo.
Right,
yeah.
So we give the same presentation basically on Devoxx Belgium in October last year. And since then, we have a few features. For example, even if Java does not support float 16 or bfloat 16, we can do inference on models that use those let's say, those float types. It's a little bit of bit hacks, so basically the way it's done, but basically it doesn't matter if Java doesn't support it. We can just, if you have a model that uses float 16 or bfloat, which is the most common for training, we can just load it and run inference just as fast as the regular models. Also, if you have a new Intel or Ryzen AMD CPU, we also support AVX 512. Without actually doing much work. So basically, we didn't have to write kernels or anything. Just adapt the vector code we have, and that's it. So basically, it works. Whatever Graal works, it will just give you the best AVX 512 instructions. And finally, the prompt evaluation uh, what I call prompt ingestion. So if you have a prompt that is fixed and it's a bunch of tokens that you know beforehand, you can ingest them, or I mean like in parallel. Inference or it's one at a time. So when you do inference, you have to do one by one. But when you do the prompt evaluation or ingestion, as I call it, you can do it many of the time. So you can batch and parallelize ingestion. So this is now done in parallel, which gives you a much better I said throughput for ingesting prompts. And yeah.
So apparently we have 5 minutes left. What if we skip this chart and we go straight to benchmarking?
Right.
So there is this beautiful chart that is also in the GitHub repo. You can look at it. It's very fascinating. But as we said, we work on a compiler with low performance, with low benchmarking, even though it is tricky to do live. And that's why we want to do a bit of benchmarking. At this point, I will transition to Alfonso. Right. And our benchmarking setup will be that we will run our engine implemented in Java, but running as a native executable against Llama, which under the hood uses Llama CPP, which as some people will tell you, it's C++, so it's native code. So there is no way you guys with Java are getting anywhere close to the native code's performance. But we want to benchmark it live and see if we can get in the same kind of ballpark with Llama CPP.
Okay, so who have heard? Who have heard of Llama? Who has used Llama? Right, kind of like the de facto, the easier way to run models locally, right? By the way, it uses Llama CPP as an inference engine, just a wrapper on top. Right. So now let's just use Llama to run like Llama. I have it installed, like serve. And now let's just run the default Llama Llama CPP Llama 3.2 1 billion parameters. So it's the default configuration. Just run it, and just let's see how it goes. Like if you like, who are you, for example? There we go. 39 tokens per second. Tell me a joke. Right. Boom. Done. Right. So let's do exactly the same model and exactly the same configuration using Llama 3.java. In this case, I will use exactly the same file. This is a GUF file. It's cached somewhere in my computer. So let's use Llama 3. I want this model, and I want to chat with it. Right. So there's one caveat here that I need to disclose because Llama CPP by default will pin or only use one thread per performance core. And the reason for this is that the Llama CPP, the way the things run, is like they assume that your CPU is a GPU. Basically, that all the CPUs or the cores are the same. So basically, it's something like we call like it's called like running like in lockstep, something like that. So basically, you run things and you expect them to be like finished like almost at the same time at the end. But if you have a heterogeneous cores like I do in this machine, and you mix both, then the whole inference engine will like bottleneck on the slower cores. Right, that's the reason why Llama CPP will like pin one thread per performance core in my machine. In Java, we don't have the limitation because this work stealing basically where when you multiply matrices, the Java runtime will adapt and feed your cores like all the work that is left. So it doesn't matter if you have faster or less or more threads. So anyway, let's run first the task set. So let's limit ourselves to use the same so the same configuration as the Llama. Here we can see like there we go. Okay, 32. That was a bit slower. Like you know, tell something like tell me a joke. Right, there we go. So in this case, it's a little bit slower. It's like 31 tokens per second. We can ask more. Who are you? Something like that. But again, so this is using the default config. So the how to say the handicapped configuration, because it's an artificial limitations in the sense that you really don't need to run with those pin cores. You can run using all the cores. Doesn't matter. So the Java runtime will just do the right thing for you. So if we run it in this mode.
We were just trying to be fair to Llama and have a very fair benchmarking setup, but if you don't impose those artificial limitations on ourselves, we are even faster. So if you can just use whatever you have available on that machine out of the box.
So the performance we get is pretty similar because, of course, what matters here is the memory bandwidth. So once your cores can like squeeze the max out your bandwidth, that's it. So that's the most performance you can get. There's a little some tricks that you can use, you know, to exactly ensure that you maximize the bandwidth, or you know like you prefetch some memory and so on. but in this case, the ballpark you get is exactly the same, or in the same ballpark compared to the C++ code. And by the way, this is native image, right? So the JIT is a little bit faster, but on native image you already get very good performance.
So the TLDR is you can have performance similar to Llama, which many people will tell you is the fastest way to run LLMs locally. And many people tell you that you need to write code in things like C++ and not in Java if you want to have good performance. That is certainly not true. Should we wrap up?
Oh, by the way, so we can also run other models. As I mentioned, there are many vendors, but all these models are cousins. They are very much alike. With some differences. For example, the tokenizers are different, and there are some minor modifications to the inference code, but very, very minor. So basically, with modified version of Llama 3.java, I can run Mistral. Actually, there's a repo to run Quen, the Gemma, the FIs, even the DeepSeek fine-tunes for the new DeepSeek reasoning fine-tunes. You can run them with this code. It runs just fine, because these models are very, very similar. There's very little differences, and it's very easy to adapt. Right.
Yeah, you can contribute to the project. There are a few areas where we particularly could use help. It's also, the code is on GitHub, so you can just go ahead and go there. But if you, and by any chance, want to be an open source contributor, those are a few directions where we could use help.
Right.
Yeah.
Well, of course, like there was this idea of we can add audio and vision to the models. Is a bit involved, but it's actually not very hard. Just need to put the work. Yeah, that's something for the future. Right, just to wrap up.
Yeah, so to wrap up, today we hopefully showed you also demos of how you can implement a fast LLM inference completely in Java. You don't need cloud-based LLMs, you don't need GPUs, you can run just completely on your local machine with CPUs, and then Java gives you all the APIs that you need for it, and then GraalVM either on JIT or in native image makes them even faster. And there is one more bullet point here that we didn't say before. I mean, the file itself, it's quite small, but also we think that this has a high educational value. It's highly commented, and if you want to learn more about implementing such projects, or if you happen to be, I don't know, teaching students, this is a fun project to teach and show them what can be done in modern Java. So with that, go ahead and scan the QR code if you want to use it yourself. And with that, we want to thank you. We will stay here for questions, but also there is upper row downstairs. We can also chat about this project down there. And with that, please rate this session, and thank you so much for your attention. Thank you for coming.